Hello everyone, welcome you back for this session on the thermal oxidation of the silicon. Now here in this case it is not with respect to the only thermal oxidation with respect to the silicon. Now here in this sessions we try to discuss with respect to the thin film depositions also, and also the wet etching and doping, and also the different methods with respect to the wafer dicing and also the wafer bonding. As we know, as I stated that the thermal oxidation of the silicon, the name itself is suggesting that the oxidation process is taking place for the silicon. The silicon dioxide is an important insulating layer which is having a major application, that too especially in the field of the electronics and as well as the MEMS. One of the prominent method in forming the high quality silicon dioxide is the reacting the silicon wafers with the oxygen, that too especially at high temperatures. On the surface of the wafers, a layer of the oxide is formed, and they separates the what we can say the interior silicon from the oxygen atoms. The atoms on the outside must be diffused through the oxide layer and reacts with the fresh silicon on the inner interface of the silicon and oxide. One can imagine that the thickness of the oxide grows as the rate of the oxidation decreases. Now, the deposition rate and as well as the utilization thickness also depends upon the what we can say the temperature range. The next concept what we are discussing is with respect to the thin deposition or thin film deposition. As you know that most of the functional materials, either it may be a conductors or it may be insulators, can be incorporated on the wafers. But before incorporating these we have to go for a process, the deposition process, which is nothing but a direct transfer of the material from the source to the wafers, either by means of atom by atom or by means of layer by layer. This it can be include either it may be a metal evaporation or by means of metal sputtering. These are the two different methods normally which are having a major applications. Now, in the process generally the conducted in a low pressure environment so that the atom may travel from the source of the wafer surface without interruption caused by means of the air molecule. For that reason only these things it should be in a vapor jar. The metal can be transferred either by means of the heating, which is called as the evaporation method. The another one is which is by means of the bombarding with a high energy ion, which is called as the sputtering. The achieved thickness and as well as the proportion to the power and as well as the time in practice is a routine. The thickness of the metal and a thin film ranges from 1 nanometer to a 2 micrometer. Now here these are the different process where the thin film deposition technologies are adopted. The first one is nothing but the evaporation method, which is represented by means of A1. The second one is nothing but the schematic diagram where the metal evaporation equipment which is inside a closed jar. The third one is by means of a chemical vapor deposition. These are the three different methods which are used to deposit a thin film. Now here in this case, in the case of the second method, that especially by placing a thin film material wafer surface in a chemical vapor deposition. As I said, the chemical vapor deposition method, which is nothing but somewhat a easier one. Two or more active species arise at the vicinity of the wafer surface. Their reactor reacts under a favorable condition, and this means that either it may be at a high temperatures or it may be at the plasma set. The reaction of these species produces a solid phase which is observed on the nearby wafer surface. Once the byproduct of the reaction may be removed by the surrounding media. The continuous reaction causes the layer of the material that it can be built on the wafer surface. The typical and also the average thickness of the what we can say the thin film deposition, especially in the case of the CVD, it can be below 1 micrometer. Now the next process what we are doing is with the wet etching. The removal of the wet etching, as the name suggests that wet etching is nothing but the removal of the material. The removal of the material by means of a wet chemical reaction is the common one. It is used, the removal of the metal, either by means of the dielectrics or by means of a semiconductors or the polymers and a functional materials. These are the different types of materials where it can be used for in the case of the wet etching method. The selectivity of the etching and also against the mask material, the substrate and the target material is a crucial issue, especially in the case of the MEMS process. While the etching rate is defined as the vertical direction and the etchant may well be attacked the layer walls of the thin film. Here in this case, the figure B shows that the etching how it is taking place. Now here in this slide, where it can be done with respect to the chemical etching and also ion, or it may be the plasma. See here if you look into that, there are so many different layers are there. These different layers, it is the first one is nothing but a film over the film. Over the film, etching stopping material is there, and then a top layer which is a red color one, that it has to be etched. That etching area, it is defined by means of a mask material. The first process is nothing but by means of a chemical etching. The second one is by means of a ion, or it may be a plasma etching. Now the doping, as the name suggests, that doping is a process of a planting or a dopant atom into a host semiconductor lattice in order to change the electrical characteristics of the host material. The dopant can be placed on the surface of the vapor, or precisely it can be injected into the what we can say the silicon lattice. This is called as ion implementation method. The dopant atoms can be further discussed at the high concentration level or even the low concentration levels also, depending upon the what we can say the type of the material. Now a desired shape of the resistor is also shown in the topmost figure. Now the resistor's features should be a moderately doped. The two ends of the resistors should be highly doped. Why these it should be highly doped means these it should be something like a metal leads, where the conductor it should be. The mask shield is first deposited and on the pattern through the window where the opening is there on the mask. The wafers are exposed to the source of the dopant, which cannot penetrates through the mask shield a layer, but can enter the silicon via the opening window only. Now here the schematic diagram explains that the black color one, where the metal leads, where the dopants it is of the higher one, and the rest of the portion is at the lower one. See now here the dopant atoms performs a random walk, or especially in the case of the semiconductors. Now the dopant atoms moves from a high concentration region to a low concentration region. This process is called as the thermal diffusion. Now the reduction in the substrate temperature during the diffusion process can be drastically decreases, and diffusivity and the what we can say the spatial extent of the dopant spreading, it is also important. The exciting doping procedures can only performed on the top surface of the vapor, and also the high temperature encountered by means of the wafer during the process, even in steps after the doping process, it can cause the dopant a redistribution and also the change in with respect to the electronic characteristics also. Now the next part is with respect to the wafer dicing. See, wafer dicing is another technology where a wafer consists of a multiple dies. Each must be broken into a separate pieces. These separate pieces, it can be done by using the what we can say a sawed disc. The traditional process of separating the dies is through by means of a dicing process. The high speed rotating dicing saw or the blade is used to cut the trenches on the silicon wafer. The cutting process is by means of a mechanical only. The wafer the water is sprayed onto the wafer, which acts as a lubricant and also removes the heat. Obviously, in this step, with the practical vibration, the water can damage the almost the free stands of the MEMS and even the mechanical components also. For that reason, the laser ablation has also been used in the case of the dicing of the wafer. Since from the 2006 or it may be in the presently, they are using the laser slit dicing, or it may be a slit dicing technology which is having advantages than that of the what we can say the wafer dicing by using the mechanical dicing method. The schematic diagram shows the where the spinning disc and as well as the wafer where the slicing has been done. The next part what we are discussing is nothing but the wafer bonding. As the name suggests that wafer bonding, wafer to wafer, the bonding it has to be done. Even here also the bonding what it is done, either it is fully bonded or it may be a partially bonded. Now either disparate materials or it may be a surface profile or even the functional characteristics to be joined to form a unique structures. As you know that the wafer bonding involves bringing of the two wafers close to a proper position and aligning to form a permanent bonding. The wafer bonding can be aided through a interfacial layer by means of a thin film deposition technology or on the wafer surface, and also the bonding allows the flexibility in processing it. The bonding process can be categorized according to the what we can say the temperature operation. The room temperature bonding, which is nothing but a low temperature bonding, and the another one is which is at the high temperature bonding. This it will be at the elevated temperatures. The bonding can be initiated the mechanical contact force, the molecular attractive forces, and also the electrostatic forces. The wafers can be chemically or mechanically modified after bonding. The wafer to wafer, the transfer has been demonstrated to achieve the surface what we can say the planarization. The planarization is also a most important, that especially to have a conductivity, and the produced device such as the mirrors or it may be membranes, even one with a larger sizes. Most of the bonding operations are conducted on the wafer scale. However, the bonding can be performed even at the die level or it may be at the device levels also, depending upon the application and also complexity with respect to the what we can say the wafer.